Welcome back to Sleepy Facts. Take a slow breath, relax your mind, rest smarter as we gently drift into tonight's story. If you'd like more quiet stories like this, you are welcome to subscribe. And if there is a topic you want to hear next, just whisper it in the comments. Tonight, we journey through time to explore one of humanity's oldest and most beautiful endeavors, the art of understanding where we are, the science of knowing how to get home, the deep human need to make sense of the space around us by drawing it, marking it, remembering it. Close your eyes and imagine yourself standing on a cliff overlooking a vast landscape. Below you, a river winds through a valley. Mountains rise in the distance. Forests stretch toward the horizon. You need to remember this place. You need to tell others about it. You need to find your way back. How do you capture this three-dimensional world on a flat surface? How do you translate the immensity of space into something you can hold in your hands? This is the question that has occupied human minds for thousands of years. The challenge of mapmaking, the art of cartography. And tonight, we'll trace that journey from the very beginning, from scratches in the dirt to satellites orbiting overhead, watching our world from space. The story of maps is the story of human curiosity. It's the story of exploration and discovery, of trade and conquest, of science and art intertwined. It's a story about how we learn to see our world not just with our eyes, but with our minds. How we learn to think spatially, to understand relationships between places, to conceive of distances we could never walk in a lifetime. Long before writing, before cities, before agriculture even, humans were making maps. We know this because the impulse to map is so fundamental, so deeply woven into how our brains work, that it seems almost instinctive. Children draw maps. They create imaginary worlds and sketch them out. They need to understand where things are in relation to each other. The earliest maps were probably not permanent. They were drawn in sand or dirt, traced with a stick, while explaining a route to another person. Gestures in the air, hands pointing and swooping to show the path of a river or the location of good hunting grounds. These ephemeral maps served their purpose and then vanished, blown away by wind or washed away by rain. But they were maps nonetheless. The oldest surviving map we have found dates back about 25,000 years. It's not drawn on paper or carved in stone. It's etched onto a mammoth tusk. Found in what is now the Czech Republic, this ancient artifact shows a landscape, a river, some mountains, valleys where people lived. The person who made this map held it in their hands during the Ice Age, perhaps using it to explain to their children where to find food, where danger lurked, where home could be found. Think about that for a moment. 25,000 years ago, in a world so different from ours, no cities, no agriculture, small bands of people moving through vast, wild landscapes. And yet, someone felt the need to create a map, to preserve spatial knowledge, to share it, to pass it on. Other ancient maps have been found painted on cave walls, carved into rocks, etched onto bones. Each one represents not just geographical knowledge, but a way of thinking, a cognitive leap, the ability to think abstractly about space, to understand that a mark on a surface can represent a place in the world, that here, on this small object, the immensity of the landscape can be captured and carried. As humans settled into permanent communities, as agriculture began around 10,000 years ago, the need for maps grew. Farming requires understanding of land boundaries. Who owns which field? Where does one person's territory end and another's begin? Early agricultural societies in Mesopotamia, in the Fertile Crescent between the Tigris and Euphrates rivers, created some of the first cadastral maps, land ownership maps, legal documents that showed property lines, field boundaries, irrigation channels. One such map, created on a clay tablet around 2300 BCE in ancient Babylonia, shows individual plots of land with their areas carefully calculated. It's not just a picture, it's a legal document, a property deed, the beginning of using maps for administration and governance, for organizing society, for settling disputes about who has the right to farm which land. The ancient Babylonians created another remarkable map around 600 BCE, known as the Babylonian Map of the World. It shows their conception of the entire cosmos. At the center, Babylon itself. Around it, other cities and regions they knew. The whole world, as they understood it, surrounded by a circular ocean. And beyond that ocean, distant, mysterious regions marked as places of myth and legend. This map tells us something profound. It shows not just what the Babylonians knew about geography, but what they believed about the structure of the universe. Their map is both practical and cosmological. It places them at the center of creation. It shows their world as they experienced it and imagined it. Every map does this to some degree. Every map reflects not just physical space, but the world view of the people who created it. In ancient Egypt, maps served different purposes. The Egyptians were masters of engineering and organization. Their civilization depended on the Nile River, on understanding its annual floods, on carefully managing land along its banks. They created maps for administrative purposes, for tax collection, for organizing labor for massive building projects. But the Egyptians also created maps for the afterlife, found in tombs, painted on coffins and papyrus scrolls. These maps showed the journey the dead would take through the underworld, the paths they must follow, the gates they must pass through, the dangers they must avoid. These were maps of spiritual geography, as important to the Egyptians as any map of the physical world. They show us that humans have always used maps not just to navigate physical space, but to understand our place in the cosmos, to make sense of existence itself. The ancient Greeks transformed mapmaking into something closer to what we would recognize as modern cartography. They brought mathematics and philosophy to the art of understanding space. They asked fundamental questions. What is the shape of the Earth? How can we accurately represent a curved surface on a flat map? How can we calculate distances we cannot directly measure? Around 600 BCE, Greek philosophers began to propose that the Earth might be a sphere. This was not based on direct observation, but on logical reasoning and mathematical principles. The idea was controversial at first, but gradually gained acceptance among educated Greeks. By 500 BCE, Pythagoras was teaching that the Earth was spherical. By 350 BCE, Aristotle provided evidence. The shadow the Earth casts on the Moon during a lunar eclipse is always circular, he noted. Only a sphere casts a circular shadow from every angle. This realization changed everything about mapmaking. If the Earth is round, then maps must account for this. You cannot simply draw the world as if it were flat and expect the distances and directions to be accurate. The challenge of projection was born. How do you represent the curved surface of a sphere on a flat piece of paper or parchment? Around 240 BCE, a Greek mathematician named Eratosthenes did something extraordinary. He calculated the circumference of the Earth. He did this with remarkable accuracy, using nothing but geometry and careful observation. He knew that in the city of Siena, modern-day Aswan in Egypt, the sun was directly overhead at noon on the summer solstice. No shadows, sunlight shining straight down into wells. But in Alexandria, far to the north, the sun was not directly overhead at that same moment. It cast shadows. Eratosthenes measured the angle of these shadows. He knew the distance between Alexandria and Syene. Using simple geometry, he calculated the Earth's circumference. His answer was remarkably close to the true value, within about 2%. 2,000 years before satellites and modern measuring equipment. This wasn't just an intellectual exercise. Knowing the size of the Earth allowed for better navigation, more accurate maps, the ability to calculate distances between cities, between continents. It transformed geography from a collection of local knowledge into a global science. Eratosthenes also created one of the first world maps based on mathematical principles. He drew lines of latitude and longitude, the first coordinate system for mapping the entire Earth. He placed cities according to their actual positions, not just their relationships to each other. His map has not survived, but ancient descriptions tell us it showed the known world from the Atlantic Ocean to India, from northern Europe to sub-Saharan Africa. Another Greek, Hipparchus, refined these ideas further around 150 BCE. He improved the coordinate system, making it more precise. He proposed that every place on Earth could be identified by two numbers: its latitude, its distance north or south of the equator, and its longitude, its distance east or west from a prime meridian. This system, refined over centuries, is still what we use today. But perhaps the most influential ancient cartographer was Claudius Ptolemy, who lived in Alexandria around 150 CE. Ptolemy wrote a book called Geographia, a comprehensive treatise on mapmaking that would dominate geographical thinking for over 1,000 years. In it, he described how to create maps using a coordinate system. He provided the coordinates of thousands of places, from Britain to China, from Scandinavia to Central Africa. Ptolemy's maps contained errors. He underestimated the Earth's circumference. He exaggerated the size of Asia. He didn't know about the Americas, of course, or about Australia, or about the Pacific Ocean, but his methodology was sound. His approach was scientific. He provided instructions that allowed anyone with the proper training to recreate his maps or to create new ones using the same principles. When Ptolemy's work was rediscovered in Europe during the Renaissance, over 1,000 years after his death, it revolutionized European mapmaking. It provided a framework, a scientific foundation that had been lost during the medieval period. It showed that mapmaking could be more than art or tradition. It could be a science based on measurement and mathematics. But let's return to the medieval period for a moment. After the fall of the Roman Empire in the West, around 500 CE, European mapmaking changed dramatically. The scientific approach of the Greeks was largely forgotten. maps became more symbolic, more religious in nature. Medieval European maps, called mappa mundi, Latin for map of the world, were not designed for navigation. They were designed to illustrate Christian theology. The most famous of these, the Hereford Mappa Mundi, created around 1300 CE, shows the world as a circle. At the top, the east, is Jerusalem, the holy city, at the center of the Christian world. At the very top of the map, beyond the earthly realm, is Christ presiding over the Last Judgment. The map shows places from the Bible: the Garden of Eden, the Red Sea where Moses parted the waters, the Tower of Babel. These are given as much prominence as actual cities and countries. Mythical creatures inhabit the margins, strange races of people with unusual features. The map is beautiful, intricate, a masterpiece of medieval art. But it would be useless for actually finding your way from one place to another. This wasn't a failure of medieval mapmakers. It was a different purpose. These maps were meant to show the spiritual significance of places, not their physical relationships. They were teaching tools, ways of illustrating religious truths. They showed the world as medieval Christians believed God had organized it, with Jerusalem at the center, with East at the top, because that's where paradise was located. While European mapmaking became more theological, other cultures were developing sophisticated cartographic traditions of their own. In the Islamic world, which stretched from Spain to India during the medieval period, scholars preserved and expanded upon Greek geographical knowledge. They created maps for practical purposes, for trade, for navigation, for administration of a vast empire. The Islamic Golden Age, roughly from the 8th to the 14th centuries, was a time of remarkable intellectual achievement. Scholars in Baghdad, Cairo, Cordoba, and other centers of learning translated Greek texts into Arabic, preserving knowledge that might otherwise have been lost. But they didn't just preserve, they added to it. They corrected errors. They incorporated new information from their own observations and from travelers' accounts. Islamic scholars had advantages that earlier mapmakers lacked. The Islamic world was vast and cosmopolitan. Merchants traded from Spain to China. Pilgrims traveled to Mecca from all corners of the Muslim world. Scholars moved between different courts and centers of learning. All of this travel generated geographical knowledge, information about routes and distances, descriptions of cities and landscapes, details about climate and resources. Islamic cartographers in the 9th and 10th centuries created world maps based on Ptolemy's work, but they added new information from their own explorations and from travelers' accounts. They mapped trade routes across the Sahara Desert, showing the path from North Africa to the gold-rich kingdoms of West Africa. They charted the Indian Ocean with remarkable accuracy, understanding the monsoon wind patterns that made trade possible between East Africa, Arabia, India, and Southeast Asia. They described the East African coast in detail, naming cities and harbors. They mapped the Arabian Peninsula, showing routes across its deserts. They described the lands of Central Asia, the Silk Road cities where goods from China entered the Islamic world. Their geographical knowledge was based on direct observation and on accounts from people who had actually traveled these routes. One of the greatest Islamic geographers was Al-Idrisi, who lived in the 12th century. Working in Sicily for the Norman king Roger II, Al-Idrisi created a world map that was the most accurate of its time. He spent years compiling information. He interviewed travelers who had journeyed to distant lands. He collected their accounts, asking detailed questions about routes and distances, about cities and landscapes, about peoples and customs. Al-Idrisi's map showed the known world from the Atlantic to China, from Scandinavia to Central Africa. It was based on information from travelers, merchants, and sailors who had actually been to these places. Al-Idrisi didn't just accept what people told him. He verified information when possible, comparing different accounts, looking for consistencies and contradictions. When reports disagreed, he tried to determine which was more reliable. The result was a comprehensive geographical work that remained influential for centuries. Al-Idrisi's map was oriented with south at the top, a convention common in Islamic cartography. This reminds us that the choice to put north at the top of maps is arbitrary, a convention that eventually became standard in European mapmaking, but isn't inherently correct. The Earth has no up or down. We decide how to orient our maps based on convention and convenience. Islamic mapmakers also created practical guides for travelers, books describing routes, distances between cities, landmarks to watch for. These weren't maps in the modern sense, but written geographical descriptions, turn-by-turn instructions for getting from one place to another. They served the same purpose as maps, helping travelers navigate unfamiliar territories. The astrolabe, an instrument that could be used for navigation and for determining prayer times, was perfected by Islamic scholars. It allowed sailors to measure the altitude of stars above the horizon, helping them determine their latitude. This was crucial for navigation, especially on the open ocean, where there are no landmarks. Islamic sailors used astrolabes and their knowledge of star positions to navigate the Indian Ocean, making long voyages out of sight of land. In China, cartographic traditions developed independently and achieved remarkable sophistication. Chinese maps dating back over 2,000 years show detailed knowledge of the empire's vast territories. The earliest surviving Chinese maps, found in a tomb dating to around 200 BCE, show military garrisons and local geography with surprising accuracy. They demonstrate that Chinese cartographers already understood principles of scale and proportion. By the 3rd century CE, Chinese cartographer Pei Xu had established 6 principles of accurate mapmaking. These principles were remarkably similar to modern cartographic concepts. He emphasized the use of a grid system for measuring distances, the need to establish scale, the importance of measuring angles accurately, and the need to account for the curvature of the Earth when mapping large areas. Pei Xu created detailed maps of the Chinese Empire that set standards for centuries to come. Chinese maps showed roads, rivers, mountains, cities, and administrative boundaries with careful attention to detail. They were used for governance, for managing the complex bureaucracy of the imperial state. They were used for military planning, showing strategic locations, defensive positions, supply routes. They were used for water management, crucial in a civilization dependent on irrigation and on controlling floods. The Chinese were particularly skilled at showing terrain, They developed various techniques to illustrate mountains and valleys, giving viewers a sense of the landscape's three-dimensional nature. Some maps showed mountains in profile, rising from the flat plane of the map. Others used shading or color to indicate elevation. These techniques made Chinese maps not just accurate, but beautiful, works of art as well as functional documents. The Chinese also created maps for administrative purposes that showed the empire's hierarchical structure, provincial boundaries, county boundaries, the locations of government offices, tax collection districts, military command areas. These maps helped the imperial government manage a vast territory with tens of millions of people. They showed who had authority over what areas, where resources could be found, how regions related to each other within the larger empire. During the Song dynasty, from the 10th to 13th centuries, Chinese cartography reached new heights. Maps became more detailed and more widely available. Printing technology, invented in China centuries before it reached Europe, allowed maps to be reproduced and distributed more easily. No longer were maps unique, hand-drawn objects accessible only to the elite. Printed maps could be owned by merchants, scholars, officials. Geographical knowledge became more democratic. Chinese world maps of this period showed China at the center, surrounded by neighboring regions. Some showed places as far away as Arabia and Africa, based on reports from travelers and traders who had journeyed along the Silk Road or sailed to distant ports. These maps reflected Chinese conceptions of their place in the world. China, the Middle Kingdom, was the center of civilization. Surrounding regions were seen as less developed, more barbarian, though still worthy of trade and diplomatic relations. In the Americas, indigenous peoples developed their own cartographic traditions. The Aztecs created detailed maps of their territories, showing towns, roads, and tribute obligations. These maps were often painted on bark paper or deerskin. They served administrative and legal purposes, documenting land ownership and political relationships. Sadly, many of these maps were destroyed during the Spanish conquest, but some survived, giving us glimpses of sophisticated indigenous geographical knowledge. The Polynesians, perhaps the greatest navigators in human history, created maps of a different kind entirely. They didn't use paper or draw pictures. Instead, they created three-dimensional maps from sticks and shells. These stick charts showed the positions of islands and the patterns of ocean swells. They were teaching tools, ways of passing on navigational knowledge. Polynesian navigators crossed thousands of miles of open ocean, finding tiny islands in the vast Pacific. They did this without compasses or sextants, using only their knowledge of stars, ocean currents, wind patterns, and bird behavior. Their mental maps were as sophisticated as any drawn on paper. They could hold entire archipelagos in their minds, understanding the relationships between islands, the patterns of winds and currents that connected them. The age of exploration, beginning in the 15th century, transformed mapmaking once again. European sailors began venturing farther from their home waters, driven by various motives: the desire for wealth, for new trade routes to the east, the desire for glory and adventure, religious zeal, the wish to spread Christianity, political ambitions, the competition between emerging nation-states for power and prestige. Portuguese explorers, sponsored by Prince Henry the Navigator, sailed down the west coast of Africa, a coastline no European had mapped before. Each voyage went a little farther than the last. They mapped new harbors, new landmarks. They learned about wind patterns and ocean currents. They discovered that sailing out into the Atlantic and then back toward the coast could help them overcome contrary winds. This volta do mar, the turn of the sea, became crucial to navigation in that region. In 1488, Bartolomeu Dias rounded the southern tip of Africa, proving that there was a sea route from Europe to the Indian Ocean. The Cape of Good Hope, he called it, though his original name was Cape of Storms, reflecting the dangerous seas he encountered there. This opened up the possibility of sailing to India, to the Spice Islands, to the rich markets of Asia, without having to cross Muslim-controlled lands. In 1492, Christopher Columbus crossed the Atlantic, seeking a westward route to Asia. He didn't find Asia. Instead, he found the Americas, continents unknown to Europeans, Africans, and Asians. Unknown to them, that is. The Americas had been inhabited for over 15,000 years by diverse peoples with complex civilizations. They had their own maps, their own geographical knowledge. But Columbus's voyage began a process that would eventually connect these previously separate worlds. The realization that these were new continents, not part of Asia as Columbus believed until his death, came gradually. Amerigo Vespucci, exploring the coast of South America in the early 1500s, argued that this was a new world, not India. The German cartographer Martin Baltimore created a world map in 1507 that showed these lands as separate continents. He labeled them America after Amerigo Vespucci. The name stuck, though it might as easily have been Colombia if history had taken a slightly different turn. Ferdinand Magellan's expedition, which set out in 1519, proved definitively that the Earth was round by sailing around it. Magellan himself died during the voyage, killed in the Philippines, but one of his ships, the Victoria, made it back to Spain in 1522, having sailed west all the way around the world. This voyage answered ancient questions. Yes, the Earth is a sphere. Yes, you can reach the east by sailing west, but it's much farther than anyone had imagined. The Pacific Ocean was far larger than early mapmakers had guessed. Each voyage brought back new information, new coastlines to be drawn, new islands discovered, new peoples encountered. Mapmakers struggled to keep up, to synthesize all this new knowledge into coherent world maps. The problem of projection became more pressing. With knowledge of the entire globe, the challenge of representing a sphere on a flat surface became unavoidable. Early world maps tried various approaches. Some showed the world in two circular hemispheres, east and west, side by side. Others used oval or heart-shaped projections. Each had advantages and disadvantages. Each distorted some aspect of reality while preserving others. Mapmakers experimented, trying to find projections that would be useful for different purposes. The discovery of the Americas also raised philosophical questions. What did it mean that European scholars, relying on ancient Greek and Roman texts, had been completely unaware of two vast continents? It suggested that ancient wisdom was not complete, that direct observation and exploration could reveal things the ancients never knew. This realization contributed to the scientific revolution, the gradual shift toward empiricism, toward trusting evidence from the senses rather than relying solely on ancient authorities. Mapping the Americas was an enormous undertaking that took centuries. The coastlines came first. Explorers sailing along coasts could map them relatively easily, but the interiors remained mysterious. Vast forests, mountain ranges, rivers winding for thousands of miles. Indigenous peoples had detailed knowledge of these lands, but that knowledge was often dismissed or ignored by European mapmakers. Slowly, through exploration and conquest, the maps filled in. But even into the 19th century, large parts of the Americas remained unmapped by Europeans. In 1569, a Flemish cartographer named Gerardus Mercator created a world map that solved one crucial problem for sailors. His map used a new projection that allowed navigators to plot a course as a straight line. If you wanted to sail from Europe to the Americas, you could draw a line on a Mercator map, measure the angle, and then sail at that constant compass bearing. You would reach your destination. This was revolutionary for navigation. But the Mercator projection had a cost. It distorted the sizes of land masses, especially near the poles. Greenland appears as large as Africa on a Mercator map, even though Africa is actually 14 times larger. The projection preserves angles, but not areas. Yet because it was so useful for navigation, it became the standard world map projection and remains common today, even though it gives us a distorted view of the relative sizes of continents as European powers established colonial empires across the globe. Mapmaking became an instrument of power and control. To map a territory was to claim it, to assert ownership even when the people living there had never consented to be ruled. To name places on a map was to assert authority over them, often replacing indigenous names with European names that honored monarchs, explorers, or religious figures. Maps showed not just physical geography, but political dominion. Borders drawn on maps became legal reality, even when those borders divided peoples and cultures that had existed there for centuries, even when those borders paid no attention to natural features or cultural boundaries. Colonial maps were tools of administration and control, showing how territories were divided up among European powers, how resources were distributed, where military forces were stationed. The Berlin Conference of 1884 to 1885, where European powers divided up Africa among themselves, was conducted with maps. Representatives sat around tables in Europe and drew lines on maps of Africa, assigning territories to different colonial powers. The people who actually lived in those territories had no say. Their own understandings of borders and territories, often fluid and based on kinship and alliance rather than fixed lines, were ignored. The boundaries drawn at Berlin, often straight lines that looked neat on maps but made no sense on the ground, still affect Africa today, contributing to conflicts and instability. But the story of colonial mapping is more complex than simple domination. Maps were indeed tools of power, but they were also products of collaboration. European explorers and surveyors in unfamiliar territories depended on local guides and informants. Indigenous people shared their geographical knowledge, sometimes willingly, sometimes under coercion. The maps that resulted combined European cartographic techniques with indigenous knowledge about rivers, mountains, resources, and routes. Often, indigenous contributions were unacknowledged. A European explorer would claim to have discovered a place that local people had known about for generations. The explorer's name would appear on the map while indigenous names were replaced or ignored. But in the details of the maps, you can sometimes see evidence of indigenous knowledge. Routes that follow paths established long before Europeans arrived. Names that are corruptions of indigenous words. Features that reflect local understanding of the landscape. The British Empire, which at its height controlled about a quarter of the Earth's land surface, put enormous resources into mapping its territories. The Survey of India, begun in 1802, aimed to create accurate maps of the entire Indian subcontinent. This was one of the largest scientific projects ever undertaken, taking decades and employing thousands of people. Surveyors traveled through jungles, across deserts, over mountains, making precise measurements. They faced dangers from disease, from difficult terrain, from political instability. Many died during the surveys. They used theodolites to measure angles, devices that allowed them to sight on distant landmarks and calculate directions with precision. They used chains to measure distances, laying them out again and again across varied terrain. They triangulated positions, creating networks of precisely located points that could serve as the framework for detailed maps. This triangulation method was ingenious. Start with one carefully measured baseline. From each end of that baseline, measure angles to a distant visible point. Using trigonometry, you can calculate the position of that point. Then use that point as part of a new triangle and repeat. Gradually, you build up a network of precisely known positions. These serve as control points for more detailed surveys. The highest peak in the world, Mount Everest, was identified and measured during this survey in the 1850s. Named after George Everest, the British Surveyor General of India, though he himself objected to the naming. The mountain was measured from a distance using triangulation. The surveyors calculated its height as 29,002 feet, remarkably close to the modern measurement of 29,032 feet. They did this without ever climbing the mountain, using only mathematics and careful observation. The mountain already had local names: Sagarmatha in Nepali, Chomolungma in Tibetan. These names meant something to the people who lived in its shadow. But European maps adopted the name Everest, and that's a name most of the world uses today. Mapping was expensive. It required trained personnel, specialized equipment, time, and political stability. The colonial powers invested so much in mapping tells us how valuable they considered these maps. Maps were essential for administration, for tax collection, for military operations, for economic development. They showed where resources were located, where roads could be built, where railways should run. They turned abstract territory into known manageable space. Throughout the 19th century, cartography became increasingly scientific and precise. New instruments were developed, better techniques for measuring distances and angles, more accurate ways of determining longitude, one of the greatest challenges in navigation. For centuries, sailors could determine their latitude fairly easily by observing the sun or stars. But longitude was much harder. you needed to know the time difference between your location and a reference point. This required accurate clocks, which didn't exist until the 18th century. The invention of the marine chronometer by John Harrison in the 1760s finally solved the longitude problem. This precise clock could keep accurate time even on a ship tossed by ocean waves by comparing local noon, when the sun is highest in the sky, with the time shown on a chronometer set to the time at a reference location. A navigator could calculate their longitude. This transformed navigation and map making, allowing for much more accurate positioning of coastlines and islands. As measurements became more precise, maps became more accurate. The coastlines of continents were charted in detail. The interiors of unexplored regions were gradually filled in. Blank spaces on maps marked terra incognita, unknown land, slowly disappeared. The 19th century also saw the rise of thematic maps. These were maps that showed not just physical geography, but data about the world, population densities, disease outbreaks, trade patterns, geological formations, climate zones, vegetation types. Each type of map revealed different patterns, different ways of understanding the world. One famous example is the cholera map created by Dr. John Snow in London in 1854. During a deadly cholera outbreak, Snow mapped the locations of cases and discovered they clustered around a particular water pump. This map helped prove that cholera was spread through contaminated water, not through air as most people believed at the time. A map became a tool for scientific discovery, for saving lives. Thematic mapping opened new possibilities. Geologists created maps showing rock types, helping to understand Earth's structure and history. Meteorologists created weather maps, tracking storms and temperature patterns. Economists created maps showing trade routes and economic data. Each map revealed patterns that might not be obvious from tables of numbers or written descriptions. Maps made data visual, spatial, easier to understand at a glance. The 20th century brought technological revolutions that transformed map making beyond recognition. Aerial photography, beginning during World War I, allowed cartographers to see the landscape from above for the first time. Military aircraft took photographs of enemy trenches, fortifications, troop movements. These photographs revealed details impossible to see from the ground: the exact layout of defensive positions, the pattern of roads and railways, the topography of unfamiliar terrain. After the war, the potential of aerial photography for civilian mapmaking became clear. Suddenly, mapmakers didn't have to laboriously survey every road and river from the ground. They could photograph vast areas from airplanes and use those photographs to create maps. A single aerial photograph could show miles of territory. Multiple overlapping photographs could be combined to create detailed maps of large regions. Aerial photography revealed details that ground surveys might miss. It showed how roads actually curved, not just their general direction. It showed how rivers actually meandered, every bend and loop. It showed how cities actually sprawled, the precise layout of streets and buildings. It made maps more accurate and much faster to produce. What might have taken years of ground survey could be accomplished in weeks or months with aerial photography. The technique required skill to interpret. An aerial photograph is not a map. It shows everything without discrimination. Buildings and trees, roads and rivers, fields and forests all appeared together. A cartographer must examine these photographs and decide what to include on the map, how to represent three-dimensional reality in two dimensions. But with training and experience, cartographers became adept at reading aerial photographs, at extracting geographical information from these overhead views. During World War II, aerial photography became a crucial military tool, used to map enemy territories, to identify targets for bombing, to plan operations. Both the Allies and Axis powers invested heavily in aerial reconnaissance. Thousands of photographs were taken daily, processed quickly, analyzed for intelligence value. The ability to see the enemy's territory from above provided a strategic advantage that could make the difference between victory and defeat. After World War II, as the Cold War began, both the United States and the Soviet Union put enormous resources into mapping the entire world. This wasn't just about mapping their own territories. It was about mapping potential battlefields anywhere on Earth. American military mapmakers created detailed topographic maps of virtually every country, often more detailed than maps those countries had of themselves. These maps showed elevation contours, allowing military planners to understand terrain. They showed roads and railways, crucial for moving troops and supplies. They showed buildings and vegetation, important for understanding cover and concealment. They were classified military resources, but they also became invaluable for civilian purposes, for scientific research, for development planning, for disaster response. Eventually, many of these maps were declassified and made available to the public. Then came satellites. The space age, beginning with the Soviet Union's launch of Sputnik in 1957, opened up entirely new possibilities for viewing Earth. Early satellites were primitive, but they demonstrated that you could observe the entire planet from space. As satellite technology improved, it became possible to take detailed photographs from orbit. In 1972, the United States launched Landsat-1, the first satellite designed specifically for observing Earth's surface. Landsat orbited the planet every 99 minutes, photographing the entire Earth every 18 days. It revealed the planet in unprecedented detail and consistency. Scientists could track deforestation, seeing exactly which areas were being cleared. They could monitor crop health, identifying areas where plants were stressed by disease or drought. They could watch cities expand, seeing the spread of urban development year by year. They could map coastlines with precision, documenting changes caused by erosion or sea level rise. The Landsat program continues today with newer, more advanced satellites. The archive of Landsat images, stretching back over 50 years, is an invaluable resource for studying how Earth has changed. Scientists can compare images from different years, watching glaciers retreat, lakes dry up, forests grow or disappear. This long-term perspective is crucial for understanding climate change, environmental degradation, and natural resource management. More satellites followed, each designed for specific purposes. Weather satellites that monitor cloud patterns, storm systems, and atmospheric conditions in real time, providing data essential for weather forecasting. Communication satellites that relay signals around the world, making global telecommunications possible. GPS satellites that form a global positioning system, allowing anyone with a receiver to determine their location anywhere on Earth within a few meters. The GPS system consists of a constellation of satellites orbiting Earth. Your GPS receiver picks up signals from multiple satellites. By measuring the time it takes for signals to arrive from each satellite, the receiver can calculate distances to each one. With distances to at least 4 satellites, the receiver can determine its exact position in 3 dimensions: latitude, longitude, and altitude. This technology, developed by the US military but made available to civilians, has transformed navigation, making it almost impossible to get lost if you have a GPS receiver. Satellite imagery also revolutionized how we think about Earth. The famous blue marble photograph, taken by Apollo 17 astronauts in 1972, showed Earth as a whole, a blue sphere floating in the darkness of space, clouds swirling over oceans, continents brown and green, ice caps gleaming white at the poles. This image became iconic, symbolizing Earth's fragility and beauty. It helped inspire environmental movements, making people think of Earth as a single, interconnected system rather than as separate nations and regions. GPS changed our relationship with maps in profound ways. For thousands of years, reading a map was a skill that required training and practice. You had to orient the map, figure out where you were on it, plot your route, navigate by landmarks. You needed to understand scale, to gauge distances, to recognize features on the map in the real landscape. It was an active engagement with geography, requiring spatial thinking and attention. Now, a GPS device can do all that for you. It knows where you are at every moment. It can calculate the best route to anywhere you want to go, taking into account current traffic conditions. It can guide you turn by turn, telling you exactly when to turn left or right. You don't need to look at the big picture. Don't need to understand the overall geography. Just follow the directions. This is convenient, enormously so. It's liberating in many ways. You can navigate unfamiliar cities with confidence. You can find obscure addresses without difficulty. You can explore without fear of getting lost. But some worry that we're losing something. The ability to read a landscape, to orient ourselves by natural features, to carry a mental map of our surroundings, to understand where we are in a larger context, not just as a dot on a screen. Studies have shown that using GPS navigation affects how our brains process spatial information. The hippocampus, the part of the brain crucial for spatial memory, shows less activity when we follow GPS directions compared to when we navigate using a paper map. Over time, reliance on GPS may affect our spatial cognitive abilities. We may be becoming more dependent on technology and less capable of navigating on our own. What happens when the technology fails? When satellites are unavailable? When batteries die? When systems malfunction? These concerns echo similar worries throughout history whenever new technologies have changed how we relate to the world. When writing was invented, people worried that it would weaken memory. When printing made books common, people worried that too much reading would be harmful. When calculators became widespread, people worried that arithmetic skills would decline. In each case, something was lost, but much was gained. The key is balance, maintaining old skills while embracing new capabilities. The digital age has brought other transformations that change our relationship with maps. In 2005, Google launched Google Earth, allowing anyone with internet access to explore satellite imagery of the entire planet. You could zoom from space down to street level. You could see your own house from above. You could virtually travel anywhere in the world, exploring places you might never visit in person. The technology was stunning, stitching together satellite images and aerial photographs to create a seamless view of Earth, adding three-dimensional representations of terrain and buildings, overlaying information about roads, borders, place names. The result was something more than a map. It was a virtual globe, an interactive model of Earth that you could explore at will. Google Maps and similar services have become essential tools for billions of people. They're constantly updated with new information. They show traffic conditions in real time, helping you avoid congestion. They integrate user reviews of businesses and attractions, crowdsourcing information about places. They show public transportation routes and schedules. They estimate travel times for different modes of transport. They combine geographical information with data about the human world in ways that previous maps never could. These digital maps are also personal in unprecedented ways. They remember where you've been, creating a timeline of your movements. They suggest places you might like based on your history. They alert you to interesting locations nearby. They adapt to your preferences and habits. In a sense, each person's digital map is unique, customized to their individual needs and interests. This raises privacy concerns. If a company knows everywhere you go, they know a lot about you, your daily routines, where you work, where you live, where you shop, where you spend your free time. This data is valuable for targeted advertising, but also potentially invasive. It can be subpoenaed by law enforcement. It can be hacked. It can reveal information you might prefer to keep private. The convenience of digital maps comes with a privacy cost that earlier generations never had to consider. We can now map things that previous generations couldn't even imagine mapping. Scientists create maps of the ocean floor using sonar to reveal underwater mountains and deep trenches. The ocean covers 70% of Earth's surface, but was largely unmapped until recently. We now have detailed topographic maps of the seafloor, showing features as dramatic as anything on land. Mid-ocean ridges where tectonic plates pull apart, deep trenches where plates collide, underwater volcanoes, and seamounts. These maps help us understand plate tectonics, plan undersea cables, locate resources, and protect marine ecosystems. We map the atmosphere using weather balloons, aircraft, and satellites to measure temperature, pressure, humidity, wind at different altitudes. These three-dimensional maps of atmospheric conditions are essential for weather forecasting. Meteorologists use them to track storms, predict their paths, issue warnings. Without these atmospheric maps, weather prediction would be little better than guesswork. We map the interior of the Earth, using seismic waves from earthquakes to understand the structure of our planet's core and mantle. When an earthquake occurs, it sends waves through Earth. Different types of waves travel at different speeds through different materials. By measuring when these waves arrive at seismic stations around the world, scientists can map the interior structure of Earth. We know Earth has a solid inner core, a liquid outer core, a solid mantle, and a thin crust. We can map variations in density and temperature deep underground. We can identify regions where molten rock rises toward the surface, creating volcanoes. We map magnetic fields, showing how Earth's magnetism varies across the surface. These maps are crucial for navigation using compasses. The magnetic North Pole, the point compasses point to, is not the same as the geographic North Pole. It moves over time, wandering across the Arctic. Magnetic field maps help navigators account for this variation. They also help scientists understand Earth's interior dynamics, the motion of molten iron in the outer core that generates Earth's magnetic field. We map gravity, measuring subtle variations in gravitational strength across Earth's surface. These variations reflect differences in density underground, have revealed hidden features. Ancient have revealed hidden features. Ancient impact craters buried under sediment. Variations in ice thickness in Antarctica. The structure of ocean trenches. We map other planets and moons with increasing detail. Mars has been mapped from orbit and by rovers on the surface. We have topographic maps showing its mountains and valleys, including Olympus Mons, the largest volcano in the solar system, and Valles Marineris, a canyon system that would stretch across the United States. We have maps showing the composition of Martian soil and rocks, where water ice exists, where past rivers once flowed. These maps guide our exploration and search for signs of ancient life. We've mapped Venus beneath its thick clouds using radar from orbiting spacecraft. Radar can penetrate the clouds, bounce off the surface, and return with information about topography. Venus has vast highland regions, volcanic plains, thousands of volcanoes. Its surface has been shaped by volcanism and tectonic activity, though very different from Earth's plate tectonics. We've mapped the moon so precisely that astronauts used these maps to navigate during the Apollo missions. Lunar maps show craters, mountains, Maria, the dark plains formed by ancient lava flows, and landing sites. They help us understand the moon's history, how it was bombarded by asteroids and comets, how its surface has evolved over billions of years. We've even begun to map exoplanets, worlds orbiting distant stars. We can't see these planets in detail, but we can detect them and infer some of their properties, how large they are, how far from their stars, what their atmospheres contain. As technology improves, we'll create better maps of these distant worlds. Perhaps one day we'll find a planet similar to Earth, and we'll map it in detail, wondering if anyone there looks back at us. The maps we create today would seem like magic to ancient cartographers. Interactive digital globes, real-time satellite imagery, three-dimensional terrain visualization, GPS navigation that knows your exact location at every moment. These would be beyond their wildest imaginings, yet the fundamental purpose remains the same: to understand where we are, to know how to get where we're going, to make sense of space, to share geographical knowledge with others. Every map is a simplification. A map cannot show everything, or it would be as complex as the territory itself, rendering it useless. The art of cartography lies in deciding what to include, what to emphasize, what to omit. A road map simplifies the landscape to show roads and highways prominently, while minimizing other features. A topographic map simplifies to show elevation and terrain. A political map simplifies to show borders and boundaries. Different purposes require different simplifications. Every map is also a perspective, a point of view. It shows the world from a particular cultural and historical position. The Mercator projection, despite its distortions, became standard partly because it was created in Europe during the Age of Exploration and served European purposes well. It centers Europe and makes northern countries appear larger than they are, reflecting European power and priorities. Other projections center other regions, show different relationships, emphasize different truths about the world. The Gall-Peters projection maintains accurate areas but distorts shapes, showing Africa and South America much larger than they appear on a Mercator map. This more accurately reflects their true sizes, but looks strange and unfamiliar to eyes trained on Mercator maps. Some argue for its use on the grounds of fairness, while others point out that shape distortion makes it impractical for many purposes. Some indigenous cartographers have created maps that center their own homelands, that use their own naming conventions, that reflect their own understanding of relationships between places. These maps challenge Eurocentric perspectives, asserting alternative ways of seeing the world. They remind us that the familiar maps we use are not neutral or objective, but reflect particular viewpoints and priorities. There is no perfect map projection. Every way of representing a sphere on a flat surface involves compromises. Every projection preserves some properties while distorting others. This is not a failure of cartography. It's a fundamental mathematical truth. The best we can do is choose projections appropriate for our purposes and understand their limitations. Maps have power. They shape how we think about the world. They influence political decisions. They can be used to claim territory, to assert control, to justify conquest. Throughout history, powerful nations have used maps as tools of empire, drawing borders that serve their interests, naming places in their own languages, erasing indigenous names and knowledge. But maps can also empower. They can help communities understand their resources and protect their rights. Indigenous peoples around the world have created maps to document their traditional territories, to fight for land rights, to preserve their geographical and cultural knowledge. These countermaps challenge official versions, asserting alternative perspectives, insisting on different names and boundaries. Maps can reveal injustices. In the United States, maps showing historical redlining, the practice of denying services to residents of certain neighborhoods based on race, have been crucial in understanding systemic inequality. Environmental justice maps show how pollution and environmental hazards are disproportionately located near poor communities and communities of color. These maps make visible patterns that might otherwise remain hidden, providing evidence for change. As you drift toward sleep, consider the journey we've traced, from scratches in the dirt to satellites in space, from local knowledge passed down orally to digital databases accessible to billions, from maps as religious symbols to maps as scientific tools, from map making as the province of specialists to mapping apps in everyone's pocket. Yet despite all these changes, the fundamental human need remains constant. We need to understand where we are. We need to orient ourselves in space. We need to know how places relate to each other. This is wired into our brains. Neuroscientists have discovered specialized cells in the hippocampus called place cells and grid cells that create mental maps of our surroundings. These cells fire when we're in specific locations, allowing us to navigate even in the dark, to remember where things are, to find our way home. We are mapping creatures. We cannot help but create mental representations of space. Every time you learn a new route to work, you're updating your internal map. Every time you give someone directions, you're sharing geographical knowledge. Every time you draw a quick sketch to show where something is, you're making a map. The maps we create externally on paper or screens are extensions of these mental maps. They allow us to share our internal geographical knowledge with others. They allow us to preserve knowledge across generations. They allow us to think about places we've never been, to plan journeys to distant lands, to understand our world at scales far beyond what we can directly perceive. Maps connect us to the explorers and map makers of the past. When you look at a map, you're engaging with thousands of years of accumulated geographical knowledge. The shape of continents, the courses of rivers, the heights of mountains, the locations of cities, all of this was painstakingly discovered, measured, recorded, and passed down. You benefit from the work of countless surveyors, sailors, explorers, and cartographers who devoted their lives to understanding the world. Maps also connect us to each other across space. When you look at a map showing distant places, you're reminded that the world is large and diverse, full of people living in landscapes different from your own. Maps can inspire wanderlust, the desire to travel and see new places. They can also inspire empathy, helping us understand that events happening far away are happening to real people in real places. As technology continues to advance, what will the maps of the future look like? We're already moving beyond flat, static maps. Virtual reality allows us to create immersive, three-dimensional maps where you can feel like you're actually walking through a place. Augmented reality overlays map information onto your view of the real world, so you can look at a street and see labels and directions floating in front of you. Maps are becoming more dynamic, more interactive, more personalized. Your map app knows your location history, your preferences, your habits. It can suggest routes based on your typical behavior. It can warn you about traffic on your usual commute before you even leave home. Maps are becoming predictive, using artificial intelligence to anticipate your needs. We're also mapping in higher dimensions. Time can be a dimension on a map, showing how places have changed over the years, or how they might change in the future. Data can be layered in complex ways, allowing you to toggle between different views, different types of information. A single location might have dozens of different maps showing different aspects: the physical terrain, the political boundaries, the population density, the economic activity, the environmental conditions, the historical changes. But with all this technology, it's worth remembering the simple beauty of a paper map, the satisfaction of unfolding a large map and spreading it out, the pleasure of tracing a route with your finger, the way a map can help you grasp the relationships between places in a way that turn-by-turn navigation never quite does. The joy of discovery when you notice something new on a map you've looked at many times before. Paper maps don't need batteries. They don't require satellites or internet connections. They work anywhere, in the wilderness, during disasters when infrastructure fails, on boats in the middle of the ocean. They're reliable in a way that digital maps, dependent on complex technology, can never quite be. There's wisdom in keeping these older skills alive, in teaching new generations how to read a paper map, how to use a compass, how to navigate by landmarks. The history of maps is a history of human ingenuity. It's a testament to our ability to observe, to measure, to record, to synthesize information. It's a story of collaboration across cultures and centuries. Greek mathematical principles, Islamic scholarship, Chinese administrative records, Polynesian ocean navigation, European exploration, American satellite technology, indigenous knowledge systems. All of these have contributed to our understanding of the world. Maps remind us that knowledge is cumulative. Each generation builds on what came before. We stand on the shoulders of giants, seeing farther because of those who came before us. The maps we use today are possible only because of the work of countless people who measured coastlines, climbed mountains, sailed uncharted waters, calculated distances, developed new instruments and techniques. And this work continues. There are still unmapped places on Earth, mostly in the deep ocean and in caves. Scientists continue to create new types of maps, finding new ways to represent data spatially. Climate scientists map temperature changes and sea level rise. Ecologists map biodiversity and habitat loss. Archaeologists use satellite imagery to map ancient cities buried beneath jungle or sand. Each new map reveals something previously hidden, expands our understanding. As you prepare for sleep, imagine holding a map in your hands. Feel its texture, paper or parchment or cloth. Notice the lines representing roads and rivers, the symbols marking cities and mountains, the colors showing different features, boundaries between nations, contour lines showing elevation, labels in various languages naming places near and far. This map connects you to everywhere it shows, to people you've never met living in places you've never been, to landscapes shaped by forces of nature and by human hands, to histories you're only beginning to understand, to futures yet unwritten. Zoom out in your mind. See the map as part of a larger collection, an atlas containing maps of every country, every region. See that atlas as part of a library, shelves filled with geographical knowledge. See that library as part of a network, connected through the internet to databases and satellites, to GPS receivers and mapping drones, to billions of people using maps to navigate their daily lives. Zoom out further. See the Earth itself from space, the perspective that satellites have given us, the blue marble floating in blackness, clouds swirling over oceans, continents brown and green, ice caps gleaming white at the poles. This is the ultimate map, the real thing, the world itself in all its complexity and beauty. But even from this perspective, we're still simplifying. We can't see the individual people going about their lives, can't see the struggles and joys, the work and rest, the building and creating that happens at every moment in every place. The map is never the territory. The representation is never the thing itself. There's always more to know, more to discover, more to understand. Rest now in the knowledge that for thousands of years, humans have worked to understand this world, to map it, to know it, to share that knowledge. You are part of that tradition. Every time you use a map, you're participating in one of humanity's oldest and most essential activities, making sense of space, finding your way, knowing where you are and how to get where you're going. The map of your own life is still being drawn. Your path through the world is unique. The places you've been, the routes you've taken, the territories you've explored. Your own mental map is unlike anyone else's. It reflects your experiences, your memories, your dreams of places you hope to visit someday. As sleep approaches, let your mind wander through places you've been. See them on the map of your memory. The home where you grew up, the school you attended, the places you've worked, the parks where you've walked, the cities you've visited, the natural places that have moved you, mountains or beaches or forests or deserts. Each place a point on the map of your life. Each memory a landmark, helping you understand who you are and where you've come from. Tomorrow, you'll wake and continue your journey. You'll navigate through space as you do every day, usually without thinking about it. You'll know how to get to the places you need to go. You'll orient yourself by familiar landmarks. You'll carry mental maps that guide you. And if you need help, you'll have access to technologies that would seem miraculous to map makers of the past. The accumulated geographical knowledge of humanity, available at a touch. But tonight, rest. Let the maps fade. Let the borders and boundaries dissolve. Let the distinctions between places soften. In sleep, you travel without moving. You visit places real and imagined. You navigate dreamscapes that follow no cartography. You're simultaneously everywhere and nowhere, unbound by geography, free from the need to know where you are, safe in the knowledge that when you wake, the world will still be there. The maps will still work. You'll still know how to find your way home. Sleep well, traveler. Rest in the confidence that humans have spent millennia learning to understand the world, to map it, to make sense of space and place. You carry that knowledge with you. You are never truly lost. There is always a way home. There is always a map to guide you. Sleep now, knowing you are exactly where you need to be. Thank you for listening with Sleepy Facts. Let your breath steady. Let your thoughts grow quiet. Rest smarter by allowing your mind to settle into the rhythm of night. If you enjoyed this moment of calm, you are welcome to subscribe. And if there is a topic you want to hear next, simply leave it in the comments. Wishing you a peaceful night and gentle dreams.